It got delayed. Don't know why.
Oh, really? Did everybody else get it yesterday? You didn't get it?
No, it's been up for a very long time.
So this happened this summer. Lin Feng
Oh yeah.
gave a talk, and
Yeah.
some people got the email, and then some people got it 2 months later.
Oh, that's weird.
And Len actually said, "Sorry, I can't come to your talk today." And, is at the same time as something else, and the talk was actually it happened 2 months earlier.
Actually, I can just minimize all
Now,
this.
if that had happened with the talk
it's
earlier
not a
this
touch
morning, that would have been of consequence. Had he been informed at the last minute.
Okay, I think we can get started. Hello everyone, thanks for coming to my talk. So this is kind of like a job interview talk I'm gonna do next week. So this is like a rehearsal. So feel free to kind of like ask any question and kind of interrupt the meeting. So today I'm going to talk about like semantic parsing. That is kind of like the structured learning problem that you're given a sentence structure and you want to kind of find a model that maps the sentence structure to a semantic graph structure. And so the task is semantic graph parsing. And so basically you're given a natural language sentence, and the goal is to kind of like parse it into some graph structure that encodes the meaning of this sentence. For example, you're given a sentence like Brian's description of himself. Like so, the output is a semantic graph structure that carries the meaning and the relations between all the entities within the sentence. So this reduced to a structured learning problem, and so we want to model the mapping from some kind of natural language string structure to the semantic graph structure. And in this talk, we mainly kind of like present three ways to do that. First one is kind of like motivated by machine translation. So we kind of like want to use some kind of synchronous grammar to kind of like synchronously analyze the string and the graph structure. And the second approach is a sequence to sequence approach. So basically, we want kind of like makes the analogy that the semantic graph is kind of like a language, and we want to kind of like use the sequence to sequence model to parse string language to the target graph language. And the third approach is kind of like some ongoing work that we are doing right now. So it's called like a cache transition system. So this is kind of like an extension of existing transition-based approach for dependency parsing. And we have some kind of like additional gadgets that are especially kind of designed for parsing graphs. And we kind of like, so this can reduce to kind of like a sequence to kind of action sequence problem. So the semantic graph representation we are using is called AMR, abstract meaning representation. So AMR is kind of like is a graph structure that has kind of like it has kind of starting from the root. We kind of like is rooted directly to the graph structure, and we can see there is a kind of different from tree because it has some kind of reentrancy. This make it a deck structure. So AMR has some nodes. We call it concepts. So concepts can be some kind of predicates or some entities within the sentence. So basically, we want to kind of like capture the relations between those entities and the predicate argument relations between them. So these kind of nodes, these concepts can be kind of like a predicate instances, such as describe 0, 1. And we also have some kind of entities like what's the entities within the sentence. And also you can be some English words like genius that map to itself. And there are also kind of relations kind of capture the relations between the entities, like so who is doing what. So this is like Ryan described himself, a genius. So this is the event of within the sentence. So yeah, so AMR relations kind of like have are taken from some kind of like different sources. It has some semantic roles that come from the prop bank, and you also have some fine-grained semantic relations that are specifically designed for AMR. So AMR now like people, so it is kind of like there are some applications of AMR that are designed for question answering, text summarization, and also semantic space machine translation. That you want to kind of map the string structure to some kind of semantics, and then based on that, add a bridge to the target language. So yeah, so let's go to the first approach. Is motivated by phrase-based machine translation. So for machine translation, you basically want to model sequence, the source sequence to the target sequence, and to kind of like analyze sequence structure, we use CFG. So to kind of do machine translation, you want to analyze both sides. So we use a synchronous context free grammar that basically, so we can see this is one example rule that here, like the first, so we can see that there are two sides for this rule. So on the left hand side, it is kind of like to CFG to analyze the source language, and on the right hand side is to kind of analyze the target side, basically. And so motivated by this approach, we want to kind of like extend the synchronous grammar to kind of like analyze the sentence and the graph structure in parallel. So on the target side, we want to kind of like have a grammar that analyzes graph structure. So we want to kind of like design some kind of graph grammar for the semantic graph side. So the graph grammar that we are interested in is called happy-edge replacement grammar. So so it is different from context-free grammar in that like it is kind of like some way to, it is edge labeled. So it is, so basically each edge here, edge label here, corresponds to basically a subgraph within the target semantic graph representation. So for example, like this x0 here corresponds to the target will eventually map to the whole graph. And so we also have this kind of like edge, hyper edge, that maps to this kind of like subgraph of within this one. So basically, we want to kind of like have some initial start edge label that we kind of like use a sequence of this kind of like rule applications to rewrite this kind of initial representation into the target graph structure. So basically, like we can kind of like think about this problem as like replacing some kind of like decomposing the graph into some kind of like subgraphs. For example, like in this way, we want to kind of like in this one, we want to kind of decompose this x0 into kind of like 3 subgraphs here that are components of this graph structure. So eventually x3 kind of like is replaced with this subgraph, and the x1 is replaced by this subgraph of the whole. So basically, you can visualize the raw application as some kind of decomposition of some kind of the whole graph structure. And so because we want to do kind of like analyze sequence and graph in parallel, so we also have a CFG side that analyzes the sentence. So basically the rules are like this. So you had kind of like source side CFG rules to analyze the sequence structure, and on target side it has some kind of graph grammar to analyze the graph structure. And so yeah, and for parsing is kind of like for parsing is reduced to kind of like a CYK kind of parsing, because we only need to, we're given a sentence, we only need to parse the sentence side to get the derivation, and we can derive the target side graph structure. So just now we kind of like just now we mentioned that we want to kind of like make the analogy that like raw applications are basically decomposition of either larger phrases into smaller phrases or larger subgraphs into smaller subgraphs. So we want to do the raw extraction, and that's basically like do that in the backward procedure. So basically, we want to kind of like start from the smallest kind of like phrase and subgraph pairs that come from the alignment from the string to the graph. And we keep composing them into kind of larger phrase subgraph pairs. So finally, when we get to the roots, is the kind of sentence AMR graph pair. So this is kind of like so if we kind of like visualize the raw application, is kind of like decomposing from the root to the naive. And basically, we want to kind of like first, given the phrase subgraph alignment, we kind of like first build all possible kind of like raw applications using this way. So so the raw application, raw extraction reduced to kind of like extract the most likely kind of like a decomposition from this forest, from this composition forest. So this kind of like so this is kind of like similar to kind of existing phrase machine translation raw extraction problem. So it's called sampling tree fragments from forest. So basically, we want to kind of like sample one way of decomposing this kind of like a graph structure. For example, like this way, this one kind of like it will decompose into this subgraph, and this subgraph. And this will represent how to rewrite this non-terminal to this 3 non-terminal. And also like, so 0, 1 basically kind of like is some binary variables that we want to kind of sample. And so that would kind of decide the boundaries of each rule. And from here, we can kind of rewrite this non-terminal with this edge in the MR graph, and also this one and this one, so on and so forth. So to do the sampling, we will use GIP sampling to do that. So basically, we want to kind of like just now we have this forest structure, so we want to kind of like sample one pass from this forest from top down, like this one. So we get like so when you have multiple choices, just know you choose one pass. That's like based on some posterior probability computed using GIP sampling. And we also kind of like some at each node, we sample kind of like a 0, 1 variable. It's also kind of like based on the posterior probability of 0, 1. And in this way, we can extract one one derivation for the synchronous SHRG. And so we do experiments on this, the very first data set for AMR. So that is 2013. And so we can see that like at that time, we only have very small data set for AMR parsing. And training set is less than 4,000 sentences. For decoding, we are using kind of like a phrase-based decoder that's using learning algorithms with cube pruning. And to evaluate so we want to kind of like evaluate how similar our predicted graph is with reference graph. So we are using a metric called S-match score. So basically, it computes the F1 of the node concepts, and also the relation tuples. So basically, like you want to kind of compare all those kind of like how much of those tuples, like entity relation kind of tuples, and how much of them match with reference graph. And so this is the results we have. So this line is our approach. And so basically, GMR is kind of the first AMR parser. So we can see that like this one achieves same result as, almost the same result as the initial one, but they further improve this. And yeah. So this is a very initial work for this kind of like grammar-based approach. And there are some, we can see that this is still kind of far from the state of the art actually. And so because we are doing kind of like so here we are kind of like interested in target representation of graph structure, but we can replace that graph structure with other kind of structures like tree structure or other semantic graph structure. And so performance does not outperform the state of the art at that time because we don't have some kind of global features, and we don't have like all the weights are not kind of like learned automatically. So and also like AMR has a specific problem of sparsity. So what is the sparsity issue? So for AMR, so most words and the concepts are really rare that only appear for a few times. And so for example, like for syntactic parsing, it only has no labels, and the target side only has like 128 symbols, and it has like 40,000 kind of sentences in the data set. And for AMR parsing, it has both node labels and also edge labels. And the target size vocabulary is more than 10,000. And the data set now is still like less than 20,000. So we can see that AMR is like way more sparse than syntactic parsing task. And so there are existing work that like reduce syntactic parsing, the structural learning problem from sequence to tree as a sequence to sequence problem. And can we do that for AMR that like maps sequence to graph structure? So that's our goal here. So so basically we want to kind of like design kind of sequence to sequence model for AMR parsing, and we want to kind of like find a way that finds some kind of like sequence equivalence of AMR structure, of graph structure. So to reduce the sparsity issue, we design kind of like use a method called categorization to kind of like generalize sparse categories. That will kind of like reduce the targeted vocabulary size. And we also have like design a supervised attention model that basically kind of like use some kind of like heuristic alignments that like different from the socket alignment from the attention model to adjust the errors made by the attention model. So so there are before this work, there are already kind of like an existing sequence to sequence parser for AMR, and it achieves extremely low performance for concerning S-match. We can see that like this is like 0.37 using a word LSTM and 0.43 for using carrier level LSTM. So carrier level LSTM and it's better than word LSTM because data set is very sparse. So carrier LSTM can kind of like can find some kind of character level prefix suffix information to reduce the sparsity. So this is first I will introduce the sequence model. So basically you have the encoder that is a bidirectional LSTM. So we want to encode the sentence, the left-to-right context using a left-to-right LSTM, and also the right-to-left context. And it also has this kind of attention, that like attention alpha, that we kind of like when predicting each output, we want to kind of condition it on all the source positions that finds out which part this output should come from, basically. And so for the encoder, so we concatenate the encoding of both directions at each position. So for example, at this one, at this position, the encoding would include the left-to-right and right-to-left encoding. Yeah, so I guess everyone is familiar with this. This is basically like how to compute the soft attention. So you just kind of like you can visualize it as some like interpolation of all the hidden state encodings. And finally, we predict each output by using a softmax. And we can see that this is greedy. So we just like predict each output based on all the previous predictions one at a time. So because the target side is a semantic graph, it's not a sequence structure. So we want to kind of like how to find a way to kind of like find some sequence equivalence of the graph structure. So we are motivated by this work that like treats the parse tree as kind of like a target sequence. So basically you are given this kind of like parse tree, and we kind of like find a way that using this bracketing structure to linearize this tree. So basically we can see that this is like similar to a stack structure that like we have this kind of the largest span is S that correspond to the whole sentence, and this will have a matching bracketing structure at this one. And also this NP phrase will have something like have this bracketing and this ends here, this phrase ends here. So basically we can kind of like restore this tree structure from this sequence structure without losing any information. So this is kind of like the trick here. And so how about semantic graph structure? So it's more difficult because like we have those kind of relations between those nodes. So our way of doing it is just like so we kind of like use the bracketing structure of the relations. So basically, I want to kind of like when we traverse the graph, we want to kind of like have some kind of start of this arc 0 that is here. That basically tells the traversal of this branch starts from here, and it ends at the right bracketing structure here. So this is like we want to kind of like start this branch by starting from this relation, and also arc1 starting from here and end here, and also the arc2 here, and this is the concept. So in this way, we find some kind of like a sequence equivalence of the graph structure. So that reduces the sequence to graph mapping to a sequence to sequence problem, and this is our graph sequence. And so because like we have tens of thousands of target vocabularies, but we only have like less than 20,000 sentences. So we know that for neural sequence to sequence, we need kind of like a really huge data set to train good neural models. So our way is to kind of like reduce the target vocabulary to make it fit the data size we have. So our way of doing that is just like we generalize all the entities, like dates, like name entities, numbers, constants, this kind of stuff into some common categories. In that way, our target site would not have kind of like the specific mentions of those entities, but categories of them. And we also kind of like map some kind of like verbs or kind of like nouns based on the frequency. If it is like not very frequent, we also map it to kind of like common post-tag categories. In this way, the basic goal is just like we want to make sure that the target site vocabulary is kind of like fits the data size we have, and we only have like 20,000 sentences. So, and because we using this kind of categorization, when we do the sequence-to-sequence prediction, the target site will also have those kind of like categories instead of the original mappings. So to do that, we kind of like first save some kind of map from those categories to the original token, and from the token, we also have some kind of like real mappings for those tokens. So we kind of like use this post-processing to kind of like to replace those kind of target site categories with the real mentions. So because the data size is very small, and we expect that like the soft attention model would behave very poorly on this small data size. So we found that like with only 20,000 sentences, the soft attention model, the alignment from the soft attention model is not very good. So we want to kind of like use some kind of other alignment to kind of make some correction of those alignments. So we use an automatic aligner with a lot of linguistic information that like so in this way, this alignment is different from soft alignment. And the soft attention vectors, this is soft alignment. So want to kind of like make sure that this heuristic alignment and the soft attention alignment agree with each other. So to do that, we kind of like change the optimization function. That like we instead of just maximize just like have the object function with entropy information. We also have the cross entropy information between the soft attention vectors and also the automatic alignments from that extracted using a lot of linguistic resources. And the cross entropy function basically makes sure that these two agree with each other. And for experiments, we kind of like evaluate on a more recent data set that's like released in 2015. So basically, it has like 20,000, 17,000 training sentences, and so evaluation is still the same for best match. So because there's some frequency, the hyperparameter of frequency that we kind of like want to reduce infrequent verbs and post-text to categories, and that frequency is tuned on depth. And we find that 15, the frequency of 15 performs the best on this data set. And so this is kind of like after the categorization, that like we can see that reducing the target side vocabulary significantly improves the performance of sequence to sequence. So that basically tells us that like if we only have like a very small data set, using kind of like predicting kind of general categories instead of the real output would kind of like help the performance of sequence to sequence. And and this is so plus supervised attention. So we can see that if we additionally use supervision from the heuristic alignment, that further improves the F-score of the sequence-to-sequence model. So, and so now we want to kind of compare our system, so sequence-to-sequence model with the state of the art. We can see that there's a huge gap between these two. So that's because like for semantic parsing is a relatively hard task that like you only have very small data set. So to do that really well, you need a lot of linguistic information to do this kind of prediction instead of just using some the data itself. And so this is two baseline sequence-to-sequence models. Even though our model improves over these two baselines, there's still a huge gap between these two. So, so why does sequence-to-sequence kind of like does behave so poorly in comparison with the state of the art? That's the problem with kind of sequence-to-sequence model. So the limitation of sequence is that it needs a very large data set to learn good soft alignments. And so for semantic parsing, because there are a lot of information to encode, so you only kind of like you need to so real linguistic experts to annotate those data. That makes the annotation very hard, and it's not like a machine translation. You can get millions of data sentences. So it's hard to annotate a large data set. And another problem with sequence-to-sequence is that during the prediction, you based on one encoder state. And when you progress, you kind of like, you based on the previous predictions and the encoder state always. But sometimes, but that will also have the limits that you don't know. You don't have the local information during the decoding. Maybe that part relates to a part of the input. So, and even though soft attention gives you the gives us the possibility to kind of like look at some input, some specific positions in the input, but in this kind of like in our scenario, because the data set is very small, soft attention does not provide that much information. That makes the sequence-to-sequence model kind of doesn't lose a lot of information in this process. So one possible solution is like using a transition-based approach. So that is incrementally processing the input into output. So we always keep a state of where we are at the input. So So this is kind of like a transition. So we already have the transition system for tree structures. So basically, you have some kind of buffer structure that you keep the words to be processed. So basically, this one will kind of like process the input words, input sentence from left to right. This is the next input word to be processed. And these words will be pushed into the stack structure. That like all the words in the stack structure are the words that we want to kind of like do some operations on. So basically, we have these operations that we shift into the stack. So reduce is basically have some kind of reduce left arc and right arc with kind of like make the edges to make arcs between the words to make it a strict tree structure. So in this way, like we kind of like so basically moving to the stack shift is just like a shift a vertex into the tree structure, and the arc operation would kind of like make links between them to make it a tree structure. So this transition system has a limit that it only deals with tree structure, and it deals with a certain type of tree structure that is called projective trees. And there are also kind of like some extensions that deal with non-projective trees. And but to do general graph structure is kind of hard. So for graph structure, you basically have to kind of make edges between all possible vertices within the graph. So one solution is kind of like some very kind of like brute force methods that like you consider all possible arcs between all those nodes, and you kind of make binary decisions between them. But this one kind of like have the complexity of O n squared. So this is kind of like behaves poorly concerning speed because like previously we have linear. So for semantic graph, it's not like any graph. So for any graph, we will kind of like imagine like this kind of graph structure. But in reality, it's like our semantic graph structure is like this. So we can see that it is very sparse. So we kind of like suspect that semantic graph structure is not that complex in comparison with tree structure. So maybe we can kind of like come up with something in between. So our goal is to design a special transition system that do graph structure kind of parsing. And so we are given a kind of a type of semantic graph, and we want to kind of like theoretically analyze this class of graphs. And so here we use kind of like a graph theoretical notion of tree width. So basically, this is kind of like a term used to kind of like describes the complexity of the graph, how complex the graph is. And so basically, so we designed this transition system to do some kind of trade-off between the speeds and also the expressiveness, like how much semantic graphs we can.
Please, I was just going to ask, how do you obtain the quantitative measures for expressiveness?
So for expressiveness, it's basically like we want to. So for transition system, we want to make sure that there is a path that kind of like you can map the sentence to the graph structure. But
with the mapping that you do between the source and the reduced representation, that the tokens in there, how they relate to each other in terms of accuracy.
Oh, so that's the problem with this one. So for the original transition system, so no matter what kind of like you can cheat, you're given the target graph, but there's no way that you can find some kind of path, a sequence of actions, this kind of actions, to process the input into that graph structure. So basically, you will fail from the very beginning. So,
okay. And so you're making the best compromise you can then.
Yeah.
Okay.
So basically, we want to kind of like design kind of a transition system that makes sure a larger ratio of the graph structure can be kind of like found by using a sequence of actions. So it's the coverage and the speed is trade-off between that. And so how complex is the graph? So this we use so some of you have taken the machine learning class. So it is called tree decomposition. So basically you are given this kind of graph structure, and you want to kind of find a tree equivalence of this graph structure. So so we can see that each node in this kind of tree basically is a subset of the original graph. So this subset, the basic intuition is just like we want to kind of like put local cliques, small cliques, into a node in this tree. In that way, we can kind of like use some graphical models or something to do kind of computation over this tree structure. So the goal is to kind of like find some kind of like local small cliques and put them into this tree structure. And we want to make sure that it has vertex cover, that basically all the vertices in the graph appears in one of the nodes, and the edge cover. So that is like each edge will appear in one pair in some node. And running this intersection means like if we have two nodes that have the same, so for example, this one and this one have vertex P in these two nodes, all the nodes on this path also have that node in this kind of like also have this vertex in this node. So we want to find the tree structure. There are algorithms that compute this tree structure given this graph structure. And so we call this one, this tree structure, the tree decomposition of this graph structure. So based on the tree decomposition, we compute the tree width of this graph. That's basically the connectedness of this graph. So basically we kind of like, for any tree decomposition of this graph, we want to find the best one that minimizes this. So basically this is the size of any node in the tree decomposition. We want to kind of like minimize this term. After that, we kind of like find some kind of interconnectedness of the graph. So for tree structure, it is 1. And for the fully connected graph that has n nodes is n-1. So we kind of like suspect that like semantic graph is much less than this term, and more close to this term. So because we are doing kind of sequence to graph mapping, so we have to follow the order of processing the strings. So that is, so because we are processing the string structure into the target graph structure, the string is basically the vertex in the target semantic graph, right? So we are given we have the constraint from the vertex of the vertices. We call it vertex order. And for tree decomposition T, we use we do kind of like a pre-order traversal and kind of source nodes. And so because we have this additional constraint from the string, we are not given all possible tree decompositions graph. It has to follow the order of the vertices of the string. So it has this additional constraint here. So this should be relatively true is RTN. So basically this term is usually kind of like greater or equal to this one. But our motivation is that we kind of think that this term, even though we are given the string constraint, this is still close to the original tree width. So so to design the specific transition system, we call it cache transition system. So for trees, we have the stack and the buffer, and now we have cache. So basically, we kind of like different from the sequence to sequence model. We have the benefit of having a configuration that tells you what state of the input you are at now. You have the stack, you have the cache, and you have the buffer. So when you predict the next output, you have all those input information available. And so here we have, so buffer is the same. It processes the input sentence. And the cache, so this is kind of like related to the tree width we have computed just now. So we have the theoretical guarantee that, like, if the relative tree width given the sentence order constraint, the tree width is m plus 1, then we can like it's m minus 1, then we can use a cache that has fixed size m to find an oracle path for mapping the sentence into the graph structure. So basically so this m is a constant, so it is fixed size. So when we kind of like process the buffer, it will be moved into the cache for kind of like processing that to make edges between the things in the cache to make a graph structure. And stack is something that like additional storage that like when we process buffer, we can move that into stack. So in this example, like the next word in the sentence is like, when we process this word, we first map it to a vertex in the AMR, in the semantic graph structure. And we also do some operation between this vertex and the vertex within the cache structure that we make edge arc0 to this concept, and also make this edge between these two want and like. In this way, we are kind of like always moving towards building a graph structure, like moving vertex into the cache, making edge between them to make it a graph, something like this. So we have two operations. One is push operation. That's basically this is hard to kind of like follow. So basically, we want to kind of like process next input in the buffer, process it and push it into the cache structure. But because the cache is fixed size, we have to make room for that new vertex. So we choose one vertex within the cache and push it into the stack. And we also have an index. For example, 1, then that basically tells you which position this vertex comes from the cache. So when we pop the stack into the cache, it will kind of be placed at the first position in the cache. So push is basically, so more formally is process the next vertex, push into the cache structure, and also choose a certain vertex in the cache at position I, and also along with the vertex itself. So it's a tuple of index and the vertex. And we also make edges that we choose a subset of vertices in the cache and make edges between the processed one and also all the vertices in the cache. And the pop operation. Pop operation is basically like we found out like the next thing in the stack can be processed next. So that would capture long-term arcs within the graph. So we kind of like pop something from the stack because we have known the index of of the next thing in the stack, we can put it into the ith position, and also we want to make room for it. That is basically we pop out the last vertex from the cache.
It's like CRISPR.
What?
It's like CRISPR for linguistics. The genetic editing tool.
What? Oh no. So this is one example. I haven't checked slides. So basically, you originally start from the cache, and in the buffer. So basically, the sentence is John wants Mary to succeed, and originally there are no edges, and so the next operation is like push, is to push the next vertex into the cache. So we choose this one, and we decided to choose the first vertex in the cache and put it onto the stack, and then we kind of like push the next word John and want, and also Mary, and the next one, this one we push two, and we found that like want is least likely to be processed next, so we put want into this kind of stack structure, and yeah. So one difference is here, when we kind of like move want into the cache, because want and John and want, it has this edge. So we also add the edge to this edge set. So also the same is here, that when we kind of like move succeed into the cache, it makes the edges between succeed and Mary, and also succeed and want. Those are the things in the cache already. So in this way, we can kind of like move the vertices of this graph into the cache, and also add edges in this process to make it a graph structure. And yeah, so to predict the actions, so we are moving towards the target graph. So at each state, we have the things from so they basically, these are the feature embeddings. We use a feed forward to predict the next action to take. And so basically, we use a bunch of feature embeddings from the state we have. That just comes from the cache, stack, and the buffer we have. And the output would have the size of all the possible actions here. So we noticed that this is kind of more suitable for semantic parsing, because the target space, the output space, becomes the number of actions instead of the output vocabulary. So we also do some kind of like experiments on some semantic graphs, and so we use AMR, same data set, and we also can do some kind of like want to extract the transition on compute the previous statistics on 200 hand-aligned sentences that has a goal alignment. So this data set has newswire and web discovery performance. So because our approach, transition system, is kind of suitable for general semantic graphs, so we also evaluate on another set of semantic graph corpus that is called comes from the SDB task of StanEval. So this is the semantic evaluation share task, and so we have 3 other semantic graph structure. That is basically this one, this one, and this one, and yeah. And the first one, we found that like for these 4 semantic data sets, the ratio width that don't have the string constraint is this one. And if we additionally have the string constraint, it's still very small constant. And because this makes the complexity to this constant times linear, so it's still linear instead of n squared. That's the basically the things we want to avoid. So and so let's get a closer look at the distribution of the tree width. So basically, like for all the semantic data set, so we can see that it is very centered on very small, like 3 and 4 for these data sets. And using this transition system, we also do some kind of like build a real parser for AMR. And so without much linguistic features, we can get to this 0.64. That is much better than the sequence-to-sequence model. And this comes from the benefit of having that kind of like state information of the input. And yeah, so basically we for the last project, so basically we kind of like build a transition system that can analyze different classes of graph structure, semantic graph structure, using the theoretical concept of tree width. And we found that like it is basically related to the cache size we have in the transition system. And most semantic graph structure we found like AMR or MRS have very low relative tree width. That means we don't really need kind of like some kind of more than linear kind of complexity to build a parser, transition-based parser for those structures. And yeah, and also kind of like our evaluation on AMR basically tells us that this parser can achieve competitive results in comparison with sequence-to-sequence models. Any question?
I have a comment on some of your early graphs that, depending on the size of the room and the size of the screen, that some of those graphs that look like they were grabbed out of papers are much smaller in font size than the text, and that they may be hard to see in a large room.
I think the synchronous hybrid replacement grammar stuff. I think that's what he's talking about.
Yeah, it was really busy, and it's depending on how it projects. If they tune it to that graph size, to that font size, that will be hard to see in a large room. And you might want to try and equalize the two. You know, this text and go all the way back to the beginning.
Okay.
And, maybe you can do it on your computer better.
Yeah. You mean the?
Some of
the
those
rules.
Yeah, right there. That for example, that would be. See the text on the right would be visible, but you know that detail might not be visible in a large room.
Okay.
And it all depends on what they use and where you're showing. I mean,
Probably you use a smaller example, like there are only 2 or 3.
Yeah, so here's what I would do. So go to the next slide. So I would put up this slide first. So get rid of the text so you can make the graph bigger.
Okay.
And then talk about what the tree is. And then show them the whole forest. And they don't have to actually read each, what's inside each node of the forest. You can just say, like, this is a representation of all the possible trees of the type that I showed you on the last slide.
Okay.
Can we go to the RSTM slide, the slide showing the equations of the RSTM?
Sure. This one. This one, right?
Yeah, I'm not sure whether it's at least something called RCM, like at the bottom of the equation, at the bottom equation, like.
Oh, you mean like you don't need this one? Or?
No, which it's not clear like in terms of the equation, like.
Okay. Yeah.
And also for context vector, they usually use C in terms of S.
Yeah.
Yeah, and for the last one, I'm not sure. Like, yeah, probably.
Yeah.
What's the problem?
He mentions like this term. So basically, there are no.
But it's better to use C instead of S prime.
Okay.
And for the last one, I think you just mentioned the output part of RCM. Yeah. But from that picture, it looks like the output part is irrelevant with the S prime. Basically, you calculate S from S prime, and you calculate the output from IST. So
I think this.
you use the attention and the ST minus 1 to calculate ST, right, from the picture.
Yeah.
And you use the ST to calculate your output, which is PYT given X and Y from 1 to T minus 1. And you should include ST prime here.
This is a concatenation. So this is special. So because like when we compute the output, we concatenate this vector with this one.
That also means, but probably this may mislead.
Yeah. Yeah, I think like for the soft attention model, different people have different variations.
Yeah, there are lots of variations. And one more question, like in your second part, like you show that you get the best performance when you tune every word which appears less than 50 times, and you say like it is the kind of achieves the best performance. But from the picture, I kind of say like you haven't tried like 1n equals to 20 or 30. Like I think 20 is already enough. Like, but my feeling is that you haven't tried.
Yeah. So at that time we just tried three combinations. So one is really large and one is middle and one is really small.
Yeah.
So.
But I think you should say that, or maybe the other people may not be convinced by your conclusion.
Yeah, so I'm a bit kind of like hesitated to put this part because I think for most people this kind of graph grammars would be kind of they might easily get overwhelmed by this kind of.
They may be confused by the kind of like x3 bar 100 something like that. They are familiar with kind of x1 x2, but for your kind of representation, for you either kind of introduce something or kind of remove them.
So basically, I just want to kind of like just briefly introduce the intuition instead of go to the specifics within each rule, which there's no kind of representations, that kind of stuff, because that's kind of like requires some kind of the people to know some grammar stuff and synchronous grammars.
Well, you could just get rid of all the 1-0 stuff, just so that people don't get distracted by that.
Okay.
And then, can you go to the slide where you have the derivation? No, go back.
Okay.
Okay, so you I think you need to explain what, like you explained at a high level that this shows a derivation, but this picture is very confusing because it's hard to tell the rules apart from the graphs. Okay, so I think the picture is okay, but you need to say like, okay, here, point to it. This is a rule, and this rule is being applied to this hyperedge and expanding it to this, and then we keep going and get the full graph out of the end. Yeah. And then, especially because you had this before, like they've never seen a rule before. So, and then you have this picture that has the rules and the graphs like mixed together, and that's not clear. So I would say maybe put up just one rule first and say a rule. This is what a rule looks like, and then here's the way you put rules together to build a full sentence.
Okay. Yeah.
I think it can also help if you use like a different type of arrow for like things that aren't in a graph.
Okay. Yeah, maybe I should use a different color.
Yeah.
Or if you use PowerPoint or anything, you can also show the rule application using animation. That is.
Oh, this is not using. This is using.
This is like it, right? You can lay out one and then you can repeat the slide. And
Yeah. It's true. But so, do you get just kind of like the correspondence between this kind of like approach and the machine translation kind of rules?
Oh, by the way, can you say like the CFC-based approach is phrase-based?
Yeah, you should say syntax-based.
Syntax-based.
Yeah.
Yeah, syntax. So. Yeah, so like, so do you guys have NLP background? Okay. So which part do you get most confusing?
I mean, there was nothing which was like too confusing because it was like fine, but I wouldn't want to. But since I don't know what are the state of the art mechanisms, I couldn't have like an intuition to compare how good your thing is against. I could just see the numbers, but apart from that, yeah. Okay. But the explanation it was
Well, I think you need to give more explanation about what the sampling is for as well. So for the so you have to say we don't. First of all, we have the graphs and strings. We don't know what the rules are, so we're trying to figure out what the rules are.
Yeah.
And for any paragraph and string, there are many possible derivations. Here's one. We put up that tree that we were just looking at. But we have to decide do we want many small rules or a few big rules, and also what should the tree structure be? And we have to, so it's unsupervised. We don't have any annotations for what the rules should be, and the basic idea is like we want rules that are useful in other sentences as well. So it's like we have to look at all of the reanalyze one sentence and then reanalyze the next sentence, and we use sampling to do that.
Okay.
And another thing that falls more in terms of future work or where you might want to go with this, and something that I would like you to read, is if you consider perhaps, there are large databases out there of images and descriptions of images, so you would not have any shortage of things to work with. But the idea of having the image as a separate source of information from the text, and and actually is the ground truth of what you're describing, and apply that as you're going through it to create a graph that is the representation of the spatial distribution within the image or the dynamic distribution within a video. And all you're doing now on the text side, but that you'd have something to serve as a ground truth that could disambiguate a lot of the things that you're running into by just extracting that from the image. So those relationships that exist in the image are the ones that are, in fact, should be described, and that would seem to me to be a way in which, I mean, and there are a lot of applications to that. I mean, in medicine, for example, the idea of the text, the free text notes in an exam note, often doesn't clearly represent what's in an image. It would be best to have a way of correcting that, so then you could make a more structured representation that you know is accurate. And there's a real need for that, and it doesn't exist today. So there are uses for that.
Yeah. Yeah, I think. Yeah, I think it would be interesting to really kind of instead of just processing the text, but also processing the image and take out objects.
And the benefit is that in a lot of the research literature, the actual image processing algorithms necessary to extract the features that you're looking for are also already there. They're not something you have to create from scratch. That you can get out all of the physical morphologies that have clinical interest, and there are algorithms that people have already developed for that. So.
Okay, thank you. Thank you.